Started, right?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay. So I'll give you a brief introduction to BJT. We'll directly go to the experiment part, right? So BJT, bipolar junction transistor. BJT stands for bipolar junction transistor. Bipolar junction transistor. So there are two types of BJTs. One is PNP and the other one is NPN. So you can see the diagrams of PNP and NPN. So here there are three regions. Okay, you can see the three regions, right? This is P material. This is also P material. Here you can see the N-type material is sandwiched between the two P-type material in PNP transistor. Similarly, P-type material is sandwiched between the two N-type material in NPN transistor. So there are three regions, and you can see the doping level also. Which one has higher level of doping from this diagram?
Sir, P.
The center region or rightmost region? See, normally the collector level doping is lesser than the emitter, but it is greater than base. Okay, I'll tell you the terminals of the transistor. So there are three regions in the transistor. One is known as emitter. The center region is known as base. This region is known as collector. So the emitter is doped higher than the collector. That is, level of doping of emitter region is greater than collector. Collector is somewhat lightly doped than the emitter, and the base, base region is very thin. You can see the base region. It means, it indicates what? The base region is very thin, right? It indicates what? What about the doping level of the base region?
Least.
Sir, it is lightly doped.
Lightly doped, yes, absolutely correct. It's lightly doped. You can see from the diagram. So the transistor has three regions, PNP or NPN. The center region is known as base region. Base region is lightly doped, and these are the terminals of the transistors: collector, base, emitter. This is a circuit symbol. So this is for PNP and this is for NPN. So you can differentiate PNP and NPN using the arrow direction. If arrow is directed up towards base, means it's a PNP. Whereas arrow is directed away from the base, means it is NPN. So can you differentiate this? Are you able to differentiate NPN and PNP? Yes or no? Are you able to differentiate NPN and PNP?
Yes, sir.
Okay, this is PNP transistor. This is NPN transistor. So transistor has two junctions. So one junction is known as emitter base junction. The other junction is known as collector base junctions. Transistor has two junctions, whereas diode has only one junction, right? Diode has only one junction. Transistor has three junctions. And so normally we apply. So in order to operate this transistor, we need some bias voltage, right? So that the carriers will drift towards the next region, and current will flow. So in order for the current to flow through the transistor, we need to apply some bias. And for transistor, normally we operate this emitter base region. Is forward bias or reverse bias from the diagram? Can you tell from the diagram? Forward bias or reverse bias? It biased in forward direction or reverse direction?
Forward.
Forward direction. This region?
Reverse.
Reverse region. So the collector base junction is reverse biased. Emitter base junction is forward biased. So what will happen when you apply a forward bias to the emitter? Here the
Right.
majority carriers are holes in the P region, right? Majority carriers are holes. So you are applying a positive potential to the emitter region. So what will happen? So this holes will be repelled by the emitter voltage, positive emitter voltage, and it will diffuse. This holes will diffuse into the N region. Very limited number of holes will be combined with the electrons in the N region, and most of the holes will reach the collector terminals. So the collector terminal, we have a reverse bias, right? So here we have connected N-type charge, N-type charge, N-type. So what will happen? This N-type charge will attract the holes coming from the emitter. So all the holes emitted by the emitter will be collected by the collector. That's why the terminal name is known as collector. So this is emitter, and very few electrons will combine with the few holes will combine with the electrons in the N region. So all the holes emitted by the emitter will reach the collector because of the negative potential reverse bias at the collector. So this is the basic operation of transistor. So for small change in the base current will cause large variations in the collector current. So this is the basic transistor action. Small change in the base current will cause more change in the collector current. So we can say that the transistor can amplify a weak signal. So transistor is basically used to amplify a weak signal. Normally the microphone signal. So when you use microphone, so the output of the microphone will be in the order of microvolts or millivolts. So this is not sufficient to drive the speaker. So you need to amplify this weak signal. So we use transistor for amplification, and the transistor has two uses. One is for amplification. The other one is it can act as a switch. For example, if you want to realize a NOT gate. So what is NOT gate? NOT gate operation. When binary 1 is inputted, what is the output?
0.
0. So it performs some inversion. So this transistor can act as an inverter. Input high voltage. Input high voltage means output is low. Suppose you are applying an input of 5 volt. So this 5 volt represents binary high, binary 1. And what will be my output? Output is 0. The output of the base collector junction is 0. That is 0 volt. So 0 volt corresponds to binary 0. 5 volt corresponds to binary 1. So we can use this transistor as a inverter also. So the transistor has two purposes. One is for amplification. The other one is for switch. These are the basic. So you understood the basic operation of transistor, right?
Yes, sir.
So this will be explained in detail in the theory class. So for lab purpose, we have to do the input characteristics of the transistor and output characteristics of the transistor. So this is the circuit connection of this is PNP or NPN. This is PNP transistor or NPN.
NPN.
So this is NPN, this is PNP. So the input junction is forward biased. You can see the forward bias. Input junction is forward biased and output junction is reverse biased. So this is the basic operation of the transistor. This is the circuit connection of the transistor. So we are going to plot the input characteristics. In input characteristics, we are going to keep the collector base VCE. This is known as voltage across collector emitter, VCE. VCE, voltage across collector emitter. So we are going to keep the VCE constant, and then we will vary this VBE, base emitter voltage. This is known as VBE. This is VBE. This is battery is VBB. Similarly, the battery is VCC. So you have to note the notations also. This is VBB. This is VCC. This is VCE, and this is VBE. Understood the difference? And notations?
Sir, can you please repeat?
Huh?
Can you please repeat?
So the input junction.
It was a bit fast.
Okay, input junction is forward biased for the transistor. Output junction is reverse biased, right? So you can see that this is NPN transistor. So the emitter is N, right? Base is P. So we have connected positive polarity to the base. So the transistor emitter based junction is forward biased. Similarly, you can see the output junction, that is collector base. So it is NPN. So the collector is N type material, but we have connected positive polarity to the N material. So it is reverse bias. So in order for transistor to operate or amplify the weak signal, we need to apply forward bias to the input junction and reverse bias to the output junction.
Okay, sir.
Understood?
Yes, sir.
And we are going to plot the input characteristics of the transistor and output characteristics of the transistor. So input characteristics means you are going to keep the VCE constant. This is VCE voltage is VCE constant, and we will vary this base emitter voltage, and we will see the we will measure the base current. That is what input characteristics. I'll show you the graph. So transistor, this is the basic relation we use. IC is equal to beta DC IB. Beta is the gain factor. IC character current is greater than the base current. You can see from this relation. Normally the beta DC is 20 to 300. So 20 times greater than the base current. So the transistor amplifies the weak signal. IC is equal to beta IB. So so this graph is the output characteristics, that is collector characteristics of the transistor. So in this, what is constant in this graph? From this graph, what is constant? So the graph is plotted between VCE and IC. So IC is the collector current, VCE is the collector emitter voltage. The graph is plotted between these two parameters, that is VCE and IC. So which one is constant?
VC.
IB is constant. So here you can see IB0, IB1. Say IB0 can be for 20 microampere. This can be 30 microampere, 40 microampere, 50 microampere, 60 microampere, 70 microampere, and this is 80 microampere, like that. So we can keep this IB to different. We are going to keep the IB for different values, and we are going to see the collector current. We are going to measure the collector current with respect to the VCE, with respect to VCE. So you can clearly see from this diagram for higher values of base current, so the collector current is increased for every increase in the base current, right? Are you able to see the graph? For every increase in the base current, you can see the corresponding increase in the collector current, right? Is that correct? Agreed? For every increase in the base current, you can see the corresponding increase in the collector current, right? This is for IB 0 microampere. This may be 10 microampere, 20 microampere, 30 microampere, 40 microampere, 50, 60, and so on, right? For every increase in the base current, you can see the corresponding increase in the collector current. So the collector current and emitter current are related by IC is equal to beta IB. This is a basic relation we are going to adapt. IC is equal to beta IB. Fine. Any questions? Any questions? Any questions? Second. So I'll Any questions?
No, sir.
Okay, I'll show you the graph for the input characteristics. I have shown the output characteristic graph. Next, I'm going to show the input characteristic graph. Just a minute. Yes, my slides are visible now. Slides are visible. Slides are visible.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we are going to use this transistor for an amplifier, right? And this is the input characteristics of the transistor. So for input characteristics, VC is held constant, and we vary the base emitter voltage, and we note the IB current. This is x-axis is VBE. Not clear, it's VBE. So we are going to vary the base emitter voltage, and we are going to see the variation of base current. So this is what we are going to do for input characteristics. And output characteristics I already told, we are going to vary the base current. We are going to keep the base current constant, and by varying VCE, we are going to see the IC. So this we are basically going to do this two plots. So first we'll do this in VLabs, and then we can do this in the LT Spice. First because it's easy to understand in LT Spice in VLabs. So you go to BJT, common emitter, BJT characteristics. So everything is description of this is given. So in simulation part, go to input characteristics. This page is loaded. Are getting this page?
Yes, sir.
Okay. So first we are going to do input characteristics. Bipolar junction transistor, common emitter, input characteristics. So what is the instruction? What is the general procedure for plotting the input characteristics? Which one is constant? Which one should be constant? Which voltage is constant for input characteristics? Which characteristics which one is constant for input
VC.
characteristics? Huh?
VC.
VCE is constant. So this is known as VCE. We can see this figure. VCE. This is VCC. This is VBE. This is VBE. The current is IB. Here it is IC. It's a NPN transistor, base collector emitter. So first we'll keep this VCE constant. So how to keep this constant? Let us keep this as what is given in the procedure. VCE 1 volt. So VCE is 1 volt. It's not any responding. Okay. VCE 1 volt. VCE 1 volt, right? Now I said VCE as 1 volt, right? VCE 1 volt, right? Have you all set this voltage? Have you all set this voltage? VCE 1 volt? Yes or no? Finish, done?
Sir, once can you share that Chrome link, sir, in the chat?
Posted in the chat box. Have you all set this value VCE of 1 volt?
Yes, sir.
Next, we are going to vary this base emitter voltage and we are going to see the base current. Right? So first you keep this. What is the steps of variation? VBE base emitter voltage will be adjusting rheostat. So you can increase this from point. So 0.1. 0.1. So collector emitter voltage is constant and I'm slowly increasing the base emitter voltage. So now it is now 0.1. Now I'll change it to 0.2. So what will happen? Base current will increase, right? This is 0.2. So you can see that when large variations will occur in the base current, now it increased from 2.326 to 2.680, right? So now you can further increase it to 3.3, 3.089. Right? Now we can further increase to 0.4. 0.4 it is 3.560. Now I'm still increasing this to 0.5. 0.5 it is 4.14 and 0.6 4.732. So after 0.7, let us see what will happen. Because for the input junction is just like a diode. So after 0.7, so you can see the increase. Now I'm increasing to 0.8. 6.2, 0.9, can you see the difference after 0.7? The base current increases slowly till 0.7. After 0.7, you can see this rise. So from 5.4 to 6.2 and 6.2 to 7.2. So 1 microampere is increased.
Sudden rise.
Sudden rise. So that's what we have plotted like this. So this is the characteristic curve. So you can see this is for VCE 0. They have done it for VCE 0, VCE 5 volt, but we are doing it for VCE of 1 volt. So if you continue this further, 1 volt. So 8.364. So this is one set of reading. So you do it for the another set of reading. 1 volt. Next you can keep this at 2 volt and 2 volt. You do it for 2 volt, at least 2 volt, so that you can compare the variations of 1 volt and 2 volt. So next you can add this and plot. You can plot this values. So we have plotted base emitter voltage versus base current microampere. Next you repeat this for 2 volt. Are you getting my point? Yes or no?
Yes, sir.
Okay, do it for 2 volt. Once done, you tell me. Finished for 2 volt.
Yes, sir. Finished.
Okay. For 2 volt, how it's coming? I will also try. So I'm clear. Now I'm setting this to 2 volt. To 2 volt. So now I'm repeating this for 0.1, 0.2, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9.
Sudden increase from point.
So after
Eight.
0.7, you can see the sudden increase. So what is the microampere current for 1 volt? That is for 0.8. The previous case. Same microamperes are coming.
8.3 something.
8.3 in earlier case.
The previous case.
For 0.8, right?
So let me check it.
What is the value of 0.8 for the previous case?
Same like 6.47.
Oh, same because
Yeah,
okay,
close.
it's almost same. And after point, okay. Okay, this is for the plot. Okay, next we'll try with the 3 volt. Let us increase this to 3 volt.
Actually, I got 6.3, sir, the previous case.
6.3. Okay.
3, yeah. Here 6.4. Now what we did, we
Yeah,
got
if you
6.8.
see when you increase the reverse bias at the collector, so we are setting the values of VCE. Now it is set to 3 volt. So we have increased the reverse bias, the collector base, collector emitter region. So let us see the response. For 0.1, 0.2, point 4, 0.5, 0.7. It's almost same, right? So we have repeated this for three values of VCE. Initially we set 1 volt, 2 volt, and 3 volt, 3 volt. Volt. Now if I increase this to 0.9,
Sir, majority of the times RS1 we keep it greater.
RF,
RS1 first resistor.
first, I'm not getting you.
Should we always keep it greater, like
Which is greater?
the one which you're adjusting, the first one, first resistor, like, for readings.
Base current, you are telling base current, right?
Yes, sir. Yes, sir.
Let's see, it's started from 2.4 to 7.4. The earlier case also same, right? Same or different? We
Close
have,
one.
what are the readings of for 0.1 for the earlier one, for the earlier case? So next you can
Some 2.6.
2 point
2.6 I got. 689. 2.68.
for 9 for 0.9
For 0.2. For 0.2. It base.
for 0.9. 0.9, you compare the readings of 0.9 of for VC 1 volt, 2 volt and 3 volt.
7.4, sir. That
Ah.
point. 7.4, sir.
For 2,
For 2, I got 2.689.
7.289.
No, sir. See, for the 0.2, I got 2.689, and for 0.9, I got 7.4, sir.
So the base current decreases for increase in the VCE. Because we are applying more reverse bias. We are increasing the reverse bias, so the potential barrier gets increased.
Base current will be the other way. We increase the second.
So this can be compared if I'll show you the another reading. If base voltage, let us keep this as below 0.7, 0.6. Let us vary this 0.1, 0.1. Point 2. So it's very closer, almost for every. But so this is the input characteristics of the transistor. In input characteristics, we keep this VCE constant, and by varying the base emitter voltage, we observe the base current. So this is a procedure for the input characteristics. So we have plotted the graph. Next, you can go to the output characteristics. In output characteristics, you have to maintain a constant base current, and you have to vary the VCE voltage, and you have to see the IC current. So for every increase in the base current, you can see the corresponding increase in the collector current. So what is the instructions given? 15 microampere, 15 to 20 microampere. So input current, please keep 15 microampere. Microampere, and vary the collector emitter voltage 0.4, 0.6, 0.7. Point 6, 0.7. So you can see the current variations in the 24 microamperes, 46 microampere. So if we increase this base current further, let us keep this base current to 20 microamperes. 20 microamperes. Now I am varying this from 0.1. 0.1. So you can see the increase in the collector current. 35. 55. So after 0.7, you can see the rise in the collector current. Sudden rise in the collector current. Are you doing output characteristics?
Yes, sir.
Okay, take two set of readings and plot the graph also. Working. Working. Working.
Yes, sir.
Okay, okay. Once done, tell me. Done. Then.
No, sir.
So VLabs. So we have verified the input output characteristics of the transistor in under common emitter configuration in VLabs. Next, we are going to repeat the same thing in LT Spice. So we have done the diode characteristics in LT Spice. In the same way, we can do this in LT Spice. Next, all of you close this VLabs now. Open LT Spice. So all of you open LT Spice now.
Okay, sir.
So LT Spice, I'll show you the new schematic. So new schematic. So all of you please follow this procedure. Procedure is same. So for NPN. On screen. On screen screen. Okay. NPN transistor. Okay. Next, we need resistors, right? Input resistor, output resistor. Just for current limiting resistor. So you can also connect with resistor, without resistor also. Next, what is required? What is required? We have transistor, and you can change this to NPN Fairchild. So 2N 2222 is a transistor number, and you can. So you require power supply, right? Voltage source. Voltage source on the input end and output end. Next, you can connect this using wires. Connections are done.
Sir, can you tell us again how to get the NPN?
Component, go to the component.
Yes, sir.
This is,
Then
this is the, I'll show you the connection. So go to the component part. In this component part, go to NPN, type NPN.
okay.
And you can change the number afterwards.
Okay. Okay.
Connections are made. An ohm resistor. This can be 30 ohm resistor. Connections are made like this.
Yes, sir.
So next, for input characteristics, which is constant? Which is constant? For input characteristic, which one is constant?
V2.
Yes, V2 is constant. So go to the simulating settings. So your first so there are various options like transient AC analysis. So we are going to study the input characteristics. So like diode characteristics, we have to choose DC sweep. In DC sweep, first source is variable, right? V1. So V1 and type of sweep is linear. Start value is 0. Stop value. Okay, 10. Increment in steps of 0.1. Then this is for the first source, and for the second source, second source is V2, right? So take V2, linear 0, stop value 10. Increment in steps of 1. Are you done with this adjustments? V1 0 to 10 volt in steps of 0.2, 0.1. V2 0 to 10 in steps of 0.1. 1. Then adjusted or not?
Sir, give voltage values also. Voltage values also.
See, V1 0 to 10 in steps of
Okay.
0.1. V2 0 to 10 in steps of 0.1. Then?
Hello, sir.
Yes.
So can you give us 2 minutes?
Okay,
I
okay.
haven't drawn the circuit.
Okay, I'll give it. Anyway, I'll repeat this, don't worry. I'm just showing this.
Increment is 1, no, sir.
Increment?
Increment value 1, no.
Okay, this is the graph. You can edit the simulation for the source 1. This is source 2. 10 millivolt. So this should be caps V1. Caps V2, first source is caps V1, 0 stop value. Okay. What error is coming?
Same error, sir.
Huh?
Same error, sir, what you got.
Non-parameter V. DC. Now there is no error, right? No error, right? Let's see. So can you see the graphs now? Can you see the graphs? Are you able to see the graphs?
Yes, sir.
So this is the input characteristics. So you can see the increase in the current after 0.7. Have you all plotted this?
Yes, sir.
So if you want to further simplify this output voltage of increment increment of 0.2. Simulate increment of increment of 3. So finished? All of you finished input characteristics?
Yes.
So next we are going to see the output characteristics. For output characteristics, you have to make one change. So you have to change this sources. Now the first source is V2. because V2 is a varying one. V2, second source is V1. Now we can check the collector current. So first source is V2, variation is 10 volt. This is increment is 1. And second source increment is 10. Simulate this 10, 20, 50 millivolt. Simulation setting. Even 5 volt. So are able to see the variations in the collector current for every increase in the base current. So this is for base current 1, base current 2, base current 3, base current 4. So you can also see after 0.7, the current becomes constant. So you can see the constant region because you are increasing the reverse bias at the collector. So after 0.7, what will happen? The collector base junction is fully reverse biased. So it levels off the further increase in the collector current. So the collector current is constant in this region. Then finished or not?
Done, sir.
Okay, the input characteristics and output characteristics of the transistor is done in the today's class. So we have done this both in LT Spice as well as in VLabs. So our next experiment will be a transistor amplifier. So we have discussed, we have verified the input-output characteristics of the transistor in this class. So the basic purpose of input characteristics is to find out the input resistance of the transistor. Similarly, for output characteristics, you can find the output resistance. I'll show you the So this is common base character. So we have done common emitter. So this is common base. This is common collector. There are three configurations of transistor: common emitter, common base, and common collector. And this is the experimental setup for the common base. So we have in lab, in actual hardware lab, we will connect these meters and ammeters, voltmeters and ammeters at the input side. Similarly, ammeters and voltmeters in the output side. And we apply the same procedure. We'll measure the voltage and current in the meters. So the purpose of the input characteristic, you can find the current gain as well as the uh, input resistance of the transistor. So input junction is forward biased. So it means that input resistance is small or high. Input resistance is small or high. Input junction is forward biased. It means
Low.
low resistance. Output junction is reverse biased. So output
High.
resistance should be high. Output resistance should be high. So you can see the graph after 0.7 that you can see the sudden increase in the current. It behaves like a diode. It behaves like a diode. After VB of 0.1, it behaves like a diode. So you can you can see the sudden increase in the current. So this is delta IE. The difference is delta IE, and corresponding difference is delta. So we can using this delta VB divided by delta IE, you will get the input resistance. So the input resistance is low, 30 ohm. You can see this 30 ohm. Similarly, if you calculate the output resistance of the transistor, it is 10 kilo ohm. So this delta VCE divided by delta IC gives you the resistance, output resistance of the transistor, and you can also calculate the current gain, delta IE divided by delta IC. So that gives the current gain. So the current gain is amplification factor is delta IE divided by delta IB. So all this thing can be obtained using in the experimentally. And this table shows the basic difference between the common base, common emitter, and common collector. Common collector configuration is rarely used, and it is used as a buffer amplifier. The current gain of the transistor, the voltage gain of the common collector is very low, so it is mainly used in impedance matching for matching the low resistance to high resistance. Normally, transistor has low input resistance, high output resistance. So for impedance matching, we use this. And so the application of common base is high frequency applications, whereas common emitter is used in audio frequency applications. And so these are some comparisons between the three configurations: common emitter, common base, common collector. So anyway, this will be explained in detail in the theory class, but we can measure the input resistance, output resistance from the graph. Actually, this PSpice is the LTSpice is difficult, but we will calculate this in the physical lab. Any questions? Any questions in common emitter, BJT? Are you clear with the procedure and purpose of input characteristics and output characteristics? Yes or no?
Yes, sir.
Okay, the next class we will try to do amplifier. So the transistor is basically used as an amplifier. So we have verified only the DC characteristics. Next, we are going to apply the signal. So you can see the signal, input signal, sinusoidal signal, and you can see the amplified output at the collector. So next we can construct this a common emitter or common base amplifier to see the how it amplifies the weak signal at the input. So that's all about this class. If you have any questions, you can ask me. Otherwise, I will take attendance and you can leave. Shall I take
No
attendance
doubt,
now? Okay, I'll take attendance. Please, all of you answer your attendance. This lab is for L45, right? L45, 46 lab, right?
No, sir.
L23 lab.
Yes, sir.
All of you are waiting for attendance only. Now you are answering. When you do experiment, no one is answering. So answer attendance, Amsika.
Present, sir.
Naman Kumar.
Present, sir.
Vivin. Vivin.
So Vivin is
Huh?
so Vivin present.
Gokul Krishna.
Present, sir.
Giridhar Prakash.
Present, sir.
Shahid Ahmad.
Present, sir.
Ankita Das.
Present, sir.
Priyanshu Bansal.
Present, sir.
Aditya Sharma.
Present, sir.
Abdul.
Present, sir.
Tejash.
Present, sir.
Pranav.
Present, sir.
Nitin Reddy. Nitin Reddy.
Present, sir.
Shivashankar Sai.
Present, sir.
C. Rohit Chaudhary.
Present, sir.
Hariharan.
Present, sir.
Amal Vishnu.
Present, sir.
Ishan Saxena.
Present, sir.
Krishna Chaitanya.
Present, sir.
Suresh.
Present, sir.
Lauren.
Present, sir.
Vishweshwar.
Present, sir.
Sanjana.
Present, sir.
Abhirami.
Present, sir.
Abhiram. Venkata Yogita.
Present, sir.
Ashit Kumar.
Present, sir.
Sriniti.
Present, sir.
Jiva.
Present, sir.
Abhigyan.
Present, sir.
1 second. Abhigyan Koshal.
Present, sir.
Edu Krishnan.
Present, sir.
Rahul Kevin.
Present, sir.
Vikram Aditya.
Present, sir.
Subrato,
Present, sir.
Sanjay,
Present, sir.
Venkatesh Varun,
Present, sir.
Ankit Singha,
Present, sir.
Kirtika,
Present, sir.
Sri,
Yes, sir. Present, sir.
Sri Rama,
Yes, sir. Present, sir.
Bhavya Yadav,
Yes, sir.
Rishikesh,
Present, sir.
Manmeet Singh,
Present, sir.
Siddharth,
Present, sir.
Nikunj,
Present, sir.
Dhananjaya Reddy,
Present, sir.
Charan Rahul,
Present, sir.
Kirat Singh,
Present, sir.
Devansh Gupta,
Present, sir.
Rahul
Present, sir.
Devanathan,
Present, sir.
Sanjupta,
Present, sir.
Rangaraj,
Present, sir.
Freddy,
Present, sir.
Meghavya, Meghavi,
Present, sir.
Rishwant,
Yes, sir.
Deepan,
Present, sir.
Gopinath,
Present, sir.
Gopika,
Present, sir.
Jervin,
Present, sir.
Mohammed Salman,
Salman, sir. Present.
Harsh Dev,
Present, sir.
Gokul Raj,
Present, sir.
Sneha,
Present, sir.
Surya Deepan,
Present, sir.
Guru Prashant,
Present, sir.
Mohammed Azim,
Present, sir.
Mohammed Sidhu,
Present, sir.
Abilan,
Present, sir.
Nitin,
Present, sir.
Maurya,
Present, sir.
Satyajit,
Yes, sir. Present.
Chantak Das.
Present, sir.
All present. Showing 59 attendees answering 70.
They left, sir.
Okay. So you can others can leave. Any questions you can ask me, otherwise you can leave.
Thank you, sir.
Thank
you, sir.
Please maintain
Thank you,
a lab copy.
Thank you, sir.
Please maintain a lab copy. I'll give you the link, you can upload it.
Thank you, sir.
Thank you all. Thank you.
Thank you, sir.